What we want to do now is move on to a thing which is kind of an application of this idea about molar mass that we've just been talking about. And then at the end we're going to talk a little bit about concentrations, and I think that's about it for today, and then there will be lots of problems in the tutorial. So, determination of something called empirical formula. What we did just before the break was we said that if you've got the formula for the compound, you can work out its molar mass, because you can look at how many of each of the different types of atoms there are in your molecule. You can work out the molar masses of each of those, and you can add them up and get the molar mass. What we're going to do here is kind of work backwards. So take some data which you can determine experimentally and work out the formula for the compound. Yeah? And in particular, we're going to work out something called the empirical formula. So often analysis of a new chemical compound will give what we call mass percentages of the constituent elements in the compound. If you are a research chemist and your business is making new stuff that no one's ever made before, which is what all the graduate students and many of the staff in the department do for their job, then one of the first things that you will do once you've made this new compound is you will take it up to a lab that's on the 5th floor of this building, where they have machines that will work out the mass percentages of carbon and hydrogen and nitrogen and oxygen and sulfur and so on that might be in the compound. In many cases, it's just a matter of weighing out some of your samples, sticking it in a machine and pushing go, and then you get back these numbers, right? But these numbers will look like this. So it could say for compound X is found to be 40.00% carbon by mass, 6.67% hydrogen by mass, and 53.33% oxygen by mass. Right? This is the sort of data you get back. From using this data, we can then work out what we call the empirical formula for compound X, where the empirical formula is just the simplest ratio of the different elements in the molecule. Now, as we'll see, the empirical formula might be a different thing to the molecular formula, the formula for the actual molecule itself. But once we have the empirical formula, then that can enable us to work out what the molecular formula is from that. So these mass percentage data that we get from this experimental technique enable us to work out the empirical formula. Okay? So what I'm going to propose is that when you do these, and I'm pretty sure there's one in the tutorial, is that you set up a wee table. There's a lot to be said for, well, I suppose this is as good a time as any to have this rant. When you do problems in chemistry, you should always write out your working. Yeah? It's another reason why I don't like these calculators, it's just mine to give you the answer. You should always write out your working, because unlike NCEA, where you get all the marks so long as you say the exact right thing, the exact right way, at the exact right time in the phases of the moon, we will give you marks for anything that you write that seems correct. If you get the right answer, then you'll get all the marks. But if you get it half right, we'll give you half the marks. And if you get it half wrong, you'll still get half the marks, because that counts as being half right. Yeah? We're always trying to give you marks. But we can only give you half the marks if we can see that you half understood what was going on. So if you just write down an answer, say it was like one of those ones previously, and you just wrote down 4 moles, and the answer was actually 3 moles, you get 0. But if you do a whole bunch of working, and at some point it all went pear-shaped, and then you ended up with your wrong answer of 4 moles, then we can follow through your thinking. And if you were kind of on the right track until right at the end, or you kind of made a silly mistake, or your calculator was set on the wrong mode and gave you the wrong answer, then we can tell that if we've got the working, and we can give you partial marks. Right? So you should always do this. Sir?
So it's not like NCA where there's
No.
section
No.
and you have to get
No.
all the parts right.
No. I think the basis upon which you should move on in all things for university, sad to say, is that it's not like NCEA.
So it's way better.
NCEA, I am told, has many benefits. But it seems to me that NCEA can work very well if you are one of the lucky few to have, for chemistry, a very good chemistry teacher. But they are not that easy to find. And if you are trying to teach to NCEA because you don't know enough to do otherwise, then it's not very good, right? So we don't care if you say the same thing but with the wrong word. We're smart enough to know what you mean, yeah? And so you'll get the marks. Okay, so for doing empirical formula calculations, what I suggest is you do a wee table like we're about to go through, because then it's all nice and clear and obvious to the person who's marking it what's going on, right? If you make it all scrawly and it's not clear, then you're less likely to win the favour of the marker to try and give you partial marks. Because remember, when you come to do first semester, there's 1,800 of you. It's a lot of marking. It's like all week. So you want to help the marker as much as you can. So you set it out nice and clearly, show all the working, and then you're good. Yeah?
Will we get lots of space for that?
You get an answer booklet to write your answers in, and you are able to get a second book or a third book or a fourth book or as many books as you want. Yes. Yes, absolutely. So what we do for these sorts of problems is we start by imagining we've got 100 grams of compound X, right? It doesn't have to be 100 grams, it could be 412 grams if you want, but it's easiest with 100 grams. So let's imagine we've got 100 grams of this compound. And what we do then is we set up this table that looks like this. We have a column for each of the three elements that we have this mass percentage data for, the carbon, the hydrogen, the oxygen. And then the first row of our table is we say what mass of that compound, of that element would there be in 100 grams of the compound. Okay? And you could argue that I've left out a line of working already, but hopefully we're okay that if it comes back that 40% of the mass of the compound is carbon, then if you have 100 grams, that means you've got 40 grams of carbon in that 100 gram sample, yeah? We're happy with that? Because percent means per 100, yeah? So we can use our mass percentage data to get these numbers pretty straightforwardly. It's going to be 40 grams of carbon and 6.67 grams of hydrogen and 53.3 grams of oxygen in our 100 gram sample, yeah? And then what we do, because remember, we can't use 40 to 6.67 to 53.3 as the ratio for working out how our molecules put together, because these are masses, not amounts. And the formula, the little numbers in the formula, are telling you about the relative numbers of each type of atom in your molecule. And this isn't about numbers yet, this is about masses. So what we have to do now is change these numbers which are in grams into numbers which are in moles, amounts of stuff, yeah? And so what we'll do now is in each case we will convert that mass in grams into an amount in moles. And we do that using our formula that we learnt about before morning tea, that the amount is equal to mass divided by molar mass. So if you do that for the carbon, it's just 40 divided by 12, it's got 12.01 now, and that comes out as being 3.33 moles. Undoubtedly that's got another 7 threes after it on your calculator. You don't have to write all those down. For the hydrogen, we can do the same thing. It's going to be 6.67 grams divided by 1.008 grams per mole. These are the numbers that you would get off. Oh, that's where I was going to photocopy your periodic tables. I did those at least. When I get you those periodic tables, I'll do that straight after the lecture, so you got them for the tube. These are the numbers you'll see on those periodic tables. Yeah. So that comes out as being 6.62 moles. And then for oxygen, you take that 53.3 grams and you divide it by the molar mass of oxygen, which is 16, and you get out 3.33 moles. Okay? And so suddenly now, hopefully, the actual ratio becomes a lot more clear. Yeah? In your 100 grams of compound, you've got 3.33 moles of carbon and 6.62 moles of hydrogen and 3.33 moles of oxygen. So now what we can do is we can work out the simplest way of expressing that ratio, 3.33 to 6.66 to 3.33. And the simplest way of expressing that ratio is 1 to 2 to 1. Yeah? It's also 2 to 4 to 2, or 3 to 6 to 3, but the simplest way, which is what the empirical formula is all about, is 1 to 2 to 1. Okay, are we happy with that? If you're not sure about how to get the ratio, then the thing to do is to find the smallest number. When you get to here, and you've got all these different numbers, is you find the smallest number and then divide everything by the smallest number. Right? Yeah?
So for hydrogen, you can't round it to 7 more. You have to give it a 6.
I wouldn't round that number to 7. No. Because remember, well, that's then not going to make this 1 to 2 to 1.
Yeah.
It's going to be like 1 to 2.2 to 1, which will end up being like 14 to 23 to 14 or some crazy ratio. That's not likely to be the way the molecule is. All right? Certainly not the ones we ask you. They're going to be sort of simple molecules. So you can do, there's a little bit of license you can take when you're going from here to here, but I wouldn't round any of these numbers here. All right? Okay. And so we could say then that the empirical formula for compound X is CH2O. So this would be the empirical formula, and in some cases that could be the formula of the molecule itself. Right? Sometimes the empirical formula is the same as the molecular formula, the formula of the actual molecule. So you can get a molecule which actually has the formula CH2O. Right? It's called formaldehyde. You may have come across this somewhere. Or methanol, if you've done lots of mindless level 3 organic chemistry. And it has that structure there, which is a little bit little. I could make it bigger, I suppose. Like that. It's a type of, well, is it an aldehyde or a ketone? I don't know. We're going to talk about these organic molecules right at the end of the course a little bit more. So for the moment, you can just say it could be that. But it could also be a larger molecule, right? It could be acetic acid. Here's the formula for acetic acid. Here's the sweet structure here. And if you work it out, that's got a formula of C2H4O2. So the ratios of the carbons to the hydrogens to the oxygens is still CH2O. But it's not actually CH2O, it's C2H4O2. Yeah? So the ratio is the same, but the actual molecular formula is twice what the empirical formula is. And just from that mass percentage data, you can't tell which of those two it is. You would have to then use other sorts of experiments to work out the difference between them. Yeah? Go on. It's also possible that the formula of the compound could be C6H12O6. Right? Do we know what that is?
Glucose.
Yeah, that's glucose, like sugar. In general, carbohydrates have the general formula C6H12O6. Right? So it could equally be sugar. And you couldn't tell. I mean, in theory, you could taste the three and then you might be able to get an idea, but that normally is a bad idea. But it could be any of those compounds, and they would still have that same mass percentage data. Yeah? So you need other techniques. Right. So to distinguish between these and other possibilities, you have to do more experiments. And the next obvious thing that you would do is you would you take a little bit of your compound and you put it in something called a mass spectrometer, which is a machine which specifically measures molar mass. Right? So if you stuck it in there, and then the molar mass came back as being 180, you go, oh, well, that's for C6H12O6. If it came back as being 30, 12, 16, 30, then you would go, oh, well, that's just CH2O, right? So the machine will work out the molar mass for you, and that, along with the empirical formula, will enable you to work out the molecular formula. We have a mass spec in the department, only at the moment it's in even more pieces than normal because it blew up last week, which was kind of a shame. So at the moment we have to ask the people in Hamilton what our molar masses are. Never mind. Is anyone from Hamilton?
Yep.
Sorry, I should stop harassing the Tron. Moving on. Okay. Right, so that's empirical formula, and I think there's going to be one of these in the tube for you to have a practice with. Okay. To be fair, that's not really something we teach you much in first semester chemistry, but it's something that's important that you know, it's kind of just an application of molar masses and stuff, so it's important you can do that. It means you understand that stuff. Okay then, on to the last little bit. We're going to finish early. I'll get in trouble. Calculate the amount of water in 1 litre of water. Okay, now this is a slightly different question because what this is calculating the amount of something in a certain volume of something else, not in a certain mass. So we can't just go amount equals mass over molar mass here because we don't have a mass. A mass is a number in grams and we don't have that in the question as it's written. What we have is a volume of water in litres. If we want to do this, then we have to have a way of converting volume in litres to mass in grams. And to do that, we need to know about something called the density of the water in this case, right? And so we've got another little formula which looks a bit like the one we had earlier, and you could do a triangle for this if you wanted, which says that the density, and the density is given this little symbol, this little Greek P, it's actually a Greek R, but we won't get into that. This is a symbol for density, and it's equal to the mass divided by the volume. So the mass of your sample of some liquid divided by the volume of that sample, of that liquid, right? And normally what we will do is we won't get you to work out the density, we'll normally give you the density and get you to work out either the volume or the mass, right? So you have to be able to rearrange that formula. And so what you could do is you could look it up. It turns out that density depends on the temperature. You might know that. As you cool water down, it becomes more dense. And so at 20 degrees Celsius, the density of water is 0.9982 kilograms per litre. So at that temperature, 1 kilogram of water weighs 0.9982 kilograms. And so this is a constant, so we would give you this. Yeah? Normally, densities are given in units of kilograms per litre, but it turns out that you can also write it as grams per mil and the number doesn't change. But kilograms per litre is the proper, correct way of expressing it. And so if you have 1 litre of water, as we do in this question, then it's kind of easy. Then you can just work out that the mass of that will be 0.9982 kilograms. Yeah? Because that's what that number tells you. 9.9982 kilograms of water per litre of water. And so that's the mass in kilograms, but of course, if we would then want to use our formula from before to convert that to an amount, we need to have that mass in grams. Hello?
What do you use for the mass and the volume to get the answer?
Sorry?
What do you use for the mass and the volume?
The mass to work out the volume.
To work out the density?
Well, we would give you the density though. In this case, well, I mean, it doesn't actually say that in the question, but we would give you the density so that you could convert a volume to a mass. Other questions you might give you both and get you to work out the density, but that's not this question. Yeah. So if 1 litre of water weighs 0.9982 kilograms, then we can also say that it weighs 998.2 grams. Yeah. Because there's 1,000 grams in a kilogram. Yes? Yeah. And so that means then that now we have a number in grams. Now we have a mass for our sample of water, and now we can use our formula from before to work out the amount. Yeah? We're going to have to work out what the molar mass of water is first. We can't look that up on our periodic table. So that's just going to be the molar mass of oxygen plus 2 times the molar mass of hydrogen So that gives you a molar mass of 18 grams per mole. And then we use our little formula. Mass divided by molar mass. So 998.2 grams divided by 18 grams per mole gives an answer of 55.46 moles. Okay? So a litre of water's got 55.5 moles in it. So 55 times 50 is 2,500. So that's marbles covering the entire surface of the Earth up to 2,500 kilometres deep. It's a lot. Okay. So we can say that 0.9982 kilograms of water contains 55.46 moles of water. And we can also say that 1 litre of water contains 55.46 moles of water, right? That's just restating what was on the previous slide. But this idea of a certain amount of stuff in a certain volume of the stuff leads us into this idea of concentration, right? So we've talked about molar masses and to work out amounts from masses. The other really important fundamental idea that you're going to have to be able to use is this business with concentration. So concentration is a measure of the amount of something dissolved or contained in a particular volume of something else. So if you like, molar mass was a way of working out the amount of something in a certain mass. Concentration is a way of working out the amount of something in a certain volume of something else. Yeah? And so we tend to be talking about solutions. I mean, we can talk about the amount of water in water, but typically we're talking about the amount of something dissolved in something else to give a solution. And so there's a couple of wee definitions here. When we're making up a solution of something, we define the thing that has been dissolved as the solute, and we define the thing that does the dissolving as being the solvent. Right? Or the thing that the solute is dissolved in is the solute. The solvent, sorry. And then it says, note that for us, the solvent will almost always be water.